Good day everyone, my name is Prottay and today I'll be presenting our work on cross-platform real-time simulation models for lithium-ion batteries in Opal-RT and Typhoon HIL. We'll begin with a brief motivation of our work. We know that we can't uh, run experiments on a real power systems, so we need real-time simulators to perform research, to monitor, to experiment on different scenarios that can happen in a power system. Now, with the advent of different types of renewable energy in our grid, like PV, like wind farm generation, like energy storage systems, with all those coming into the picture, we'll need good and accurate mathematical models for PVs, energy storage systems, and wind farms on real time simulators. And to get or to implement a good energy storage system model, we need to have an accurate battery model. So, in this current research, we are implementing a battery model, a lithium-ion battery, which is very common in this kind of applications. Additionally, we need to note that the real-time simulators are not particularly standardized yet. So, one of the aims of our work was to make our battery model cross-platform compatible and homogeneous. So, these are the contributions of our work. We proposed a simple battery model. We implemented it in Simulink and compared the results with the archived benchmark battery model. Then we took our model to Opal-RT, that's the real-time implementation of the MATLAB model, and then we compared those results with the real-time simulation results of the benchmark model too. So once this comparison validates our model, we migrate our model to a completely different hardware, Typhoon HIL. Once Typhoon HIL model is implemented, we compare the Typhoon HIL results with our Opal-RT results, and when they match, we conclude that our model is cross-platform compatible and homogeneous. Now that model is placed inside a small microgrid model just to show that our model can work within a larger system. This implementation is just an example implementation that's been carried out in Typhoon HIL. So the battery model we propose here is made available on GitHub. In this overview slide, we will introduce the differences between the two hardware architectures. As shown, one of them uses Intel processors, one of them uses ARM R-class processors, one of them utilizes RTLab, one of them utilizes HIL SCADA and Typhoon schematic editor. And our model under test was the custom battery model. It was tested under charging condition, under discharging condition, and it was also tested inside a demo microgrid model. Our proposed battery model is, as we mentioned, library independent, reasonably hardware efficient, quite accurate, and it's able to compute the state of charge in real time as well as the terminal voltage. In this slide, sorry, in this slide we are showing the actual battery model, the circuitry of it. On left, the benchmark model proposed by Yao and Aziz initially. On left hand side, the benchmark model is shown. The left half of the benchmark model practically represents the state of charge. It's modeled by a capacitor in parallel with a current source. If the model is not connected to any actual load, a R self-discharge is introduced through which the battery can discharge very slowly. The remaining part of the model is modeled by a voltage source, a dependent voltage source in series with a resistor. That resistor's model is quite intricate. Additionally, in the benchmark model, we have two RC units which model the transient small signal performance of the battery. In our model, we have completely removed those RC units because those transient parts were not relevant for our implementation. This makes our model simplified, and since the capacitances are removed, we need to do less number of integrations and it's computationally less cumbersome from the simulator point of view. Now we take our model and put it into an algorithm. Like, we need to make the proper block diagram to compute all the units, compute all the parameters. So we had like three inputs, that is initial state of charge, the battery capacity, and nominal voltage. And we have the two outputs, that are final state of charge or the present state of charge and the present output terminal voltage. The series resistance is a function of the state of charge, and it's computed by an exponential model, and all these computational equations are reported in Yao's paper, as we cited before. Now we are doing the experiments. So we are comparing our proposed model with the MathWorks benchmark model here. We can see that both under charging and discharging conditions, our model performs fairly closely to the benchmark model. For discharging, the terminal voltage shows a minor mismatch of 0.3 volts, but it's nothing to be gravely concerned about. Now we know that our model is accurate, but is it efficient? So in this slide we are showing that our proposed model is, in terms of efficiency, is comparative with the MATLAB's benchmark model. In all honesty, our model is a little bit slower and a little bit larger. Why so? Because we are concerned about cross-platform compatibility. So our model does not use any sophisticated library element. We are using computational blocks like multipliers, dividers, maybe for loops. There's nothing sophisticated about them. We are not taking any library element from Opal-RT, and which makes our model larger, and there's no internal optimization carried out as they do in most of their library elements, and our model becomes a little slower, which is okay because our model is still perfectly competitive. Now we reproduced our model in Typhoon HIL, and we can see that the results are perfectly matched. Why these results are so perfect? Because there were no library dependency to be worried about. We took numerical functions from one hardware and we re-implemented them in the other. So charging, discharging, terminal voltage, state of charge, all of them are perfect. Now how does our model work inside a bigger model? So in our case, the bigger model was a microgrid that utilizes a diesel generator, a PV system, and has a load. It's a 12.4 kilovolt microgrid, like a medium voltage level, and the intricate details of the controllers, the governor, the PV unit's inverter, its controller, those things are not shown in this simple diagram. Now we are implementing a step change of 12.5 kilowatt in the load in the microgrid model, and we can see and that the battery responds to it. The battery has to respond to it because the governor is operating at a fixed operating point. So is the PV. So the increased demand in the load must come from the battery. So we can see that the battery is giving more output power. Um, it's a perfect step increase in the response of the power. In terms of the current should increase a significant step, and we can also see there are some transient oscillations in the current response, which is perfectly expected. The voltage shows a minor dip of like 5 voltage, which is nothing to be concerned about, and the state of charge decreases constantly, which is also expected when the battery is in discharging mode. Now, where do we stand? Our model is can be implemented in two different hardwares, but we need to go further, and we plan to extend it towards Modelica and a standard FMI standards. That will make our model truly universal. Another part of the work is to test the microgrid model with the battery in it in different scenarios. We just showed a step response. We need to do different kinds of faults, loss of generation, loss of load, swing. A lot of things can be done and needs to be tested. For this paper, we just showed the step response just to exhibit and demonstrate that our model can work inside a bigger model. So thank you for listening.